Hello, hello. Is this? No idea which is on and which is off. All right. Thank you for coming to my talk. Now, I prepared this talk. I prepared some notes, and you can find them here at this QR code. And then this morning there was a very good talk by Exorio, who covered pretty much everything that I'm going to talk about. So it leaves me kind of in a bit of a spot, but I thought instead of sort of recovering the stuff, I could do that. I could see if you've been paying attention and ask you questions about that. But rather than do that, I'm going to diverge quite considerably from my notes here. So, yeah, there'll be some stuff here that I'll talk about, but I'll just, probably ad-lib a lot of this. To start with, in fact, I think I shall start talking about my T-shirt. So, on my T-shirt, I've got some maths. And these are essential bits of maths that you need for zero-knowledge proofs. So I'm quite lucky because I've got the T-shirt. So if I need some emergency maths, I can just look down, and there I've got the equations. I've got the sum check protocol. I've got Shamir secret sharing, all the good stuff. But most people don't have this. Actually, if you want a T-shirt, you come and talk to me. You can have one. But most people don't have this. They don't have experience of the maths. So we're all pretty much beginners when it comes to ZK. And this is kind of a bad situation to be in, because then we're very much reliant on experts to help us with security. And security is very much a social good. We all want the security to be there. It's to everybody's benefit that we have good security in our applications. So what I'm sort of appealing for here is that we need better education and we need better tooling so that we don't have to rely so much on advanced cryptographers to help us and make our code secure. And in fact, a lot of this landscape is changing. The application landscape in ZK is changing. We're getting a lot of people coming in who want to write Cairo contracts, who want to write contracts on Mina. That's just become possible this week. And there's certainly been some effort and write Noir contracts on Aztec. And there's been effort, particularly with Noir, I think, to try to abstract away the zero-knowledge aspects so that the developers don't have to know that. So we are heading, I guess, in the right direction, but there are still things that those developers need to know and best practices that they need to know. The motivation for this, part of it is with ZK, a lot of the work has gone into ZK roll-ups and layer 2s, and there is a lot of TVL there. So there's a lot of a big target for people who could break these kind of systems. So there's certainly the motivation to have good security in ZK, but it's certainly not easy. Now, ZK itself has a couple of features. So you could say that ZK is all about computational integrity. So it's all about proving that a piece of code ran correctly, was executed correctly. You could also say it's all about privacy. These are two features. You don't have to have one or the other. You can have them both. In some cases, some of this is ignored on Starknet. They don't care about the privacy. Everything is public, but that is still possible. The features of ZK, well, essentially, ZK is about an interaction between a prover and a verifier. These are the roles that we have. We kind of change that a little bit because when we use it with blockchain, we kind of squash the interaction, so we're not going back and forth. But if you want to understand ZK, it often helps to think of it as the prover and the verifier having some kind of conversation and passing messages back and forth. And it's useful to think about the motivations of these people. So the prover is making some kind of claim. That could be the claim that they know something, or in the case of roll-ups, it could be the claim that we executed this transaction and we did it correctly. And I'm going to prove to you that that's the case. The prover wants that proof to be accepted. That's really their motivation. But also, it could be the case that there's some privacy involved. So there may be some secret involved. They may have some secret input to the proof, and they certainly don't want the verifier to know that. So that's the prover's motivation. On the verifier side, they are going to be cynical about what the prover is saying, hopefully. They're going to be saying, okay, I've got the proof, but I'm not just going to take your word for it. I've got to be able to check this. I've got to be able to do it in a very rigorous way. But they will know that they're going to do this in zero knowledge, so they know that they're not going to find out the secret that the prover has. Okay. So we potentially have this interaction, and if you read the literature, and if you look at the sort of the theoretical sort of models around this, we're kind of assuming that these are different people and that they're kind of in conflict somehow, which is strange because the situation we're in now, or we're in a strange situation now, because what we actually have with something like roll-ups is we have the prover there creating their proofs that the execution of this transaction was done correctly, and they send that proof off to the layer 1, gets picked up by the verifier contract, and the verifier contract says, yep, that was fine. But the same people wrote the verifier contract as wrote the proving system on the layer 2. So at the moment, we're not, although it's possible to be doing the checking, we don't really need to do that. You could just have sent it and just be trusting the people who are there anyway, the people who wrote this. And going forward, when we move to more decentralized systems on the layer 2, when we get more decentralized sequencers and decentralized provers, we maybe have proving markets, and you're giving other people the ability to create the proofs, we may be in for a shock, because then suddenly we're going to get back to this idea that actually we do need to be very careful about the possibility of real cheating going on. Okay, but to just introduce some terms that you see, for a proving system, or a zero-knowledge proving system, we have two main aspects that are regarded as crucial. One is called completeness. This is kind of the happy path. And what this means is that if you're a prover and you create a correct proof, then it will be accepted. And we want that. That's the happy path. The second one here, soundness, this is really to prevent cheating. And what we're saying is that if we have a dishonest prover and they send off an incorrect proof to the verifier, then the verifier will be able to detect that that's not correct. They will be able to reject it with a high probability. This second part, it is more probabilistic, and there are kind of bounds on it. We're making assumptions about what the prover is able to do. We're saying that they have bounds on the computation that they have. They can't have an infinite amount of computational resource. They can't have an infinite amount of time. And we will sort of set that bound, and then we'll say, well, our system will work given that. Okay, so that's what you may hear about with those two terms. And then also, obviously, we want the zero knowledginess. We don't want the verifier to be able to reverse engineer the proof in any way and find out what's any secret input that the prover had. Okay, now, why does it get tricky? Well, when we're actually building these things, the way we've built them is using finite fields. We use a kind of a restricted set of maths to do this. And this certainly makes the cryptographer's life easier. We can more easily make claims about what is happening. We have better representations of the items within our proofs, shorter, more easy to handle. But then it does make things a little bit difficult for the developers. So when you're developing your zero-knowledge proving system, or you're writing an application on it, you have to be aware that you're working on a finite field. That means you're working on a set of integers. There's a maximum value. We're using modular arithmetic. If you forget that, then you can start to get into some problems, and that's where we see some of the problems happening. If we start to think what an attacker could actually do, well, they could break privacy, so that's a fairly big thing that could go wrong. But also, they could, well, maybe that's going, so that's the zero-knowledge aspect, and then they could also break the soundness aspect. So they could create a false proof. So on your roll-up, you could create a proof that this transaction executed correctly, but actually it didn't. Or maybe something like Zcash, you could be creating Zcash out of thin air, but the system will be saying, yeah, this is all fine, these transactions are all okay. Now, why is this different in ZK than in traditional applications? Well, I think because we've got this idea of it being a proof, a very rigorous mathematical proof is what we're producing. Therefore, we take more risks with it. We think that we can take more risks with our system, much more so than if I'd written a solidity program and I said, yeah, this is the answer to something, please believe me. You probably would want to check the code and all that kind of thing. But if I present a zero-knowledge proof and say, there you are, just accept that, and there's a lot of maths behind this, you're probably going to be, okay, well, I'll take more risk on that. So we have to be careful when we're doing ZK. Potentially there's more at risk because we're making bigger claims about what we've done. Oh, that's not very big. Okay, but this is the ZK snark process. Okay, just to give you an idea of what's going on when we create a proving system and we actually create a proof. So I hope it's visible. If not, well, please shout. So the first part really is this part here, where we're setting up the system. This was mentioned earlier, the fact that when for a snark, so a particular type of zero-knowledge proving system, we have a setup. It relies on a thing called a common reference string, and this needs a bit of randomness in it, which has to be kept secret. If that wasn't kept secret, then we could create false proofs, or someone could create false proofs. So there's an elaborate ceremony to make sure that everything's kept secret. You have to be careful about that. Anyway, but that's part of the setup. We have that. We also have this thing called a circuit. When we are writing an application in these zero-knowledge systems, we start off, maybe we write a Cairo contract. Okay. What that Cairo contract is doing is essentially checking some claim, checking that something is being done correctly. That gets transformed into a circuit. This is just a different representation, a more easily provable or manipulable representation of a higher level language. But that is part of the setup of our system. So we have that, and we have the setup with the common reference string. And once we've got that, then we can start to use our system. And using our system then involves someone giving some inputs to the system, so maybe some public inputs, some private inputs. There could be a complicated part where we have to manipulate that. If the prover is just saying, I know the square root of 25, that's a simple witness. The witness, is the secret part that the prover is claiming. It's the thing they want to keep secret. So if it was just something like that, that's simple. In the case of a roll-up, though, what we're doing is we're saying, well, we executed this transaction, and the witness here is going to be all the details of that execution. And so putting that into our system could be a bit complex. But anyway, we do that. We then go through this, what's called the back end, which is where the interaction would be going on, where the prover and the verifier would be going back and forth, and the prover would be saying, here you go, here's the proof, please believe it, and the verifier would be saying, well, I'm not so sure, send me some more details, etc. But the result of all that, this is the proof, will be that the verifier would accept it. Now, I've spoken about interaction. Actually, in the case of the systems we have this way of squashing down the interaction into one step. So we have non-interactive proofs, because really it wouldn't work on a blockchain if we had to have the contract going back to the prover and the prover sending more information, etc. That just wouldn't work. So we have it all in one step, and hopefully the verifier is going to say, yeah, that was all good, I accept your proof. Okay. Is that okay? All right, good. So where do we get problems? This is just some examples. So this is from paper. There's a great paper, a system of knowledge about vulnerabilities in ZK, which tells us where most of the problems that we have found have been found. Okay, that poses all sorts of questions. You find things where you look for them, etc. But anyway, this is where the things tend to have been found. Lots in the circuit, and I guess that's why people are concentrating on circuits and talking about circuits. And the types of problems we get, we're not getting problems so much where the prover is not getting their proof accepted. That's the completeness thing. We're tending to get problems where the prover could cheat. So that's why we've got many more in this column, and not much on the zero knowledge side. I can't read this, I'm going to go over here. Okay, so these, the next few slides actually were done much better this morning, so I would suggest you have a look at those. I'm not going to repeat these, but yeah, these are very well-known examples. What they have in common, I'll explain about CIRCOM. So these are all written using the CIRCOM library, and that's a very low-level way of creating a circuit. CIRCOM has been around for a while, so it is widely used. There's lots of good templates out there. That's great. But the developers coming in now are probably going to be using other things. Where they're going to be using Cairo, they're going to be using Noir, O1JS. They're not going to be going down to such a low level when they're writing their circuits. And we're going to have to, if you're thinking of security problems and examples, we're going to need to think of the examples from those languages and not just about CIRCOM. But so it does illustrate some good things. So one of the main points, and in fact the non-deterministic is really a subset of the under-constrained circuit, is the idea that when the circuit is checking what the prover is claiming. Okay, so the prover is saying, I know the square root of 25, and we write a circuit to see if that is actually the case. If we have an under-constrained circuit, what that means is we've kind of left a gap, we've left too much leeway for the prover to actually input something that would be accepted as a correct proof, but isn't actually a correct proof. So when you write your code, and this applies not just to CIRCOM, but also to these higher-level languages, you have to be sure that you are exactly testing everything that the prover is claiming, and you're not giving them any leeway whatsoever. Okay. The non-deterministic is just kind of a subset of that. Yeah, I won't explain more about that. Okay. Also, we need to be careful about underflows and overflows. We're working on finite fields, so what you can get, if you're not careful, is you could overflow, you could go past the largest number on the finite field, it will wrap around, and then you'll get some arithmetic that maybe you didn't expect, or that gives you an acceptable result where it shouldn't. So that's, this is the example here where we're saying that we're looking for a particular value, and we've got two possible inputs, two situations that would produce the correct value. So you have to be careful about that. And in these types of systems, what you often have are, when you're doing arithmetic, you're doing range checks. You're checking that the values you have lie within a particular range, and therefore couldn't do overflow or underflow. This was covered earlier. I won't go into that. This was covered earlier. This is about things being optimized out. I guess that's down to the compiler, really. That we should be careful about that. We need better tooling to help us with that. This one, the frozen heart, this was about the final step. When we've got our interaction going on, but we don't want that, we're going to squash it down. The way that we do that is using a technique called the Fiat-Shamir heuristic. It's a common technique used in zero-knowledge proofs, but it can be used with other types of systems. It has been misapplied quite widely, or it was realized that this was misapplied quite widely. It's similar really to the idea that we've got under constrained code. When they used it, they weren't including enough information in some of the steps, and therefore it could have been exploited. So yeah, that's what that was about. The trusted setup leak, that's really this point I said, for some types of zero-knowledge proving systems, for the snarks, they need this trusted setup. It relies upon this common reference string. That needs some secret value. We don't want that to leak, so we do an elaborate ceremony, a multi-party computation, where the people involved mustn't collude. If they do, and there's a leak, then you could create a false proof. The classic example, I think, or the one talked about this morning, was with Zcash, and there's an error in the paper, but they managed to fix it, and as far as we know, everything's okay. Yeah, these were all, I think these were all talked about, so I won't go further. We do have some tools, as you can see here, that help us. I'm sorry if this is not very, very large, but it does give you an idea of some of the techniques that can be used. But I still think that we're really early days here with some of these tools and what they can provide. Yeah, that's pretty much it. Just about us. We do auditing, so we do Solidity Cairo, we're about to start with Mina. We run audit courses as well. If you want to talk to us, there's some details of that. These notes are at that QR code. If you want a T-shirt, come and talk to me. But I'm happy to answer questions if you have them, because I did want this to be a beginner's guide to these kinds of problems. And so, yeah, please do ask questions, because I'm sure I didn't explain it well. That's the best kind of question, yeah.
Maybe it doesn't make sense.
Okay.
So you showed us this circuit, this very simple example, and now, if I understand correctly, you're building a circuit that is able to capture what the EVM is doing. So you're building a circuit for the EVM.
Yeah.
And I'm just curious, how complex can these circuits become? In some metrics, maybe you can give me some lines of code metrics or something like that.
Yeah, okay, so that's a very good question. Yeah, these circuits, I think they're called circuits. They look a little bit like electrical circuits. They're made of things called gates, and we use those because we can do any kind of computation with them. In terms of the number of gates we can do, you're talking sort of millions of gates that can be used. All the time, these things are improving, and we're getting better. We can do larger circuits. But performance and the kind of limits on circuit size is a factor. And when you're writing code, you will sometimes be limited by that and not be able to write code as expressively as you would like, or have such complex code as you would like. So yeah, there is definitely a limit there. I'm sorry, I've forgotten the rest of your other question, but does that answer?
Yeah, what would a circuit for the EVM?
Yeah, so these are very complex indeed. And the way they are written, there's some really good stuff from Scroll. They've got a lot of good documentation which shows you what their circuits are like. And what they do is they have like a general circuit, but then there's lots of sub-circuits that look at particular aspects. So you'd have a circuit that is all about the storage of the EVM. And then that would rely on, for example, a circuit that does hash functions and can do the Merkle-Patricia tree. And so you get all of these sort of independent little circuits then joining together. But they are very complex indeed. And the actual implementation, what that looks like, is you have these huge tables where the circuit is represented. We want to constrain what can happen, and each constraint is represented as a row in this table. But they are absolutely huge, and lots of rows. And your code kind of goes through these rows, and there are various rules about it. But yeah, so they can be huge. Go on.
With languages such as Cairo, do you still have some issues that are specific to zero knowledge, or is that abstracted away, kind of?
Yeah, so that's a good point. The common bit I see, they've done a really good job, and I really take my hat off to the people who wrote these languages. It's an amazing achievement to abstract all of that stuff. But where things still tend to kind of poke through from the zero knowledge world is with like data types. You're restricted in the data types that you can use in these languages. So typically there's a thing called a field element, the native data type, and that will be of a certain size. And often this is not quite 2 to the 256, which would be really useful because in Solidity that's the native data type. So in Cairo, for example, we have a structure set up which has 2 parts to it of 2 to the 128, because we can't quite do it all in one field. And so you have to have a structure of 2. But that's the area that tends to be. Other areas are around things like loops, and that I think that was mentioned earlier as well, and some things to do with branching as well. That's quite often hard to represent. But some languages do it better than others, and so some languages you can kind of get away with quite a bit. But certainly data types is, I think pretty much every language has that problem. Yeah. All right. Cool. All right.